A cosmic secret hides where even light cannot escape. Black holes are the universe's ultimate enigmas, regions of gravity so intense they trap everything. But our common understanding barely scratches the surface. By the end of this journey, your entire perspective on these celestial monsters will be completely reshaped. We will uncover if they are truly bottomless pits or perhaps gateways to other realities. What is the final, terrifying fate of anything that falls in? What single mystery of the cosmos most captures your imagination? Gravity is not a vacuum. This is the first great misconception we must shatter. We often picture black holes as relentless cosmic drains, actively sucking in everything across the universe. But their pull is not some special supernatural force. A black hole's gravity operates under the exact same rules as our own sun's. Its power comes purely from its immense mass compressed into an unthinkably small point. Think of it this way: if you could, by some impossible magic, swap our sun for a black hole of precisely the same mass, a terrifying change would occur, but not the one you might expect. The sky would go dark and all life would freeze, of course, yet our planet itself would not be yanked from its path. Earth would continue to orbit that spot of perfect darkness year after year, following the same elliptical path it always has. The force of gravity from the central mass would be identical. So what then is the difference? What makes a black hole so fearsome is not the strength of its pull from a distance, but the nature of its core. The true point of no return is a boundary known as the event horizon. This is not a physical surface you could touch. It is a mathematical threshold, a one-way street woven into the fabric of space itself. Outside this boundary, you could still, in theory, fire your rockets and escape the gravitational grip, just as a spacecraft can break orbit from a planet. But once any object, even a single particle of light, crosses that invisible line, its fate is sealed. Not because it is being sucked in, but because the space within that horizon curves so severely that every possible path leads inward toward the central singularity. There are no roads leading back out. The universe itself at that point offers no exit. So the danger lies not in some exaggerated pulling power, but in coming too close to a boundary from which the laws of physics provide no return ticket. That invisible boundary of the event horizon protects us from the true strangeness within. For decades, we have pictured the final destination, the very core of a black hole, as a singularity. This is the word science uses for a point of infinite density, where all the collapsed matter is crushed into a speck so small it has no dimensions at all. It is a place where the mathematics of gravity spirals into nonsense, and the known laws of the universe simply stop working. But what if this ultimate endpoint is not the final word? New ideas from the cutting edge of physics are challenging this classical nightmare. Theories like loop quantum gravity propose that the crushing force may hit a fundamental limit before reaching an impossible infinity. Instead of a dimensionless point, the heart of a black hole could be a bizarre object known as a Planck star. This would not be infinitely small, but a compressed ball of matter resting at the smallest possible size the universe allows, a scale so tiny it is almost beyond comprehension. The implications of this shift are staggering. If there is no true singularity, then matter is not destroyed. It is merely transformed into a state of extreme density. This opens a door to even wilder possibilities. Some physicists speculate that this dense core could act as a bridge, a cosmic tunnel warping through the fabric of reality to another place, or even another universe entirely. The black hole would then be not a pit of annihilation, but a gateway. We are forced to confront a profound mystery. At the very heart of these cosmic monsters, space and time as we understand them may not just be bent, but may cease to exist entirely. What new laws of physics would govern such a realm? The answer remains locked behind the event horizon, a secret the universe is not yet ready to give up. That classic picture of a black hole as a perfectly simple object is itself an illusion. For years, the dominant theory in physics was the no-hair theorem. It suggested that a black hole is the ultimate cosmic bald head, stripped of all complexity. No matter what you threw into it, whether it was a star, a spaceship, or an entire library of books, the black hole would erase all evidence of those things. It would only remember three simple numbers: its mass, its electric charge, and its spin. Everything else, every detail about what made the fallen object unique, would be permanently lost behind the event horizon. This idea, however, creates a catastrophic problem. It violates a fundamental law of quantum mechanics, the principle that information can never be truly destroyed. You can burn a book, but in theory, if you could collect every single ash particle and trace every wisp of smoke, you could reconstruct its every word. The information still exists in the universe, just in a different form. The no-hair theorem suggested black holes were the one exception, the ultimate shredders of reality, erasing information forever. This is the black hole information paradox, a deep and troubling conflict between our two best theories of physics, general relativity and quantum mechanics. But what if black holes are not so bald after all? New theoretical work suggests they might possess what physicists poetically call quantum hair. This is not literal hair, of course, but a proposed subtle structure, a kind of intricate fingerprint etched into the gravitational field just outside the event horizon. This quantum hair would be a permanent record, a gravitational memory of everything that ever fell in. The unique properties of a star that was consumed would leave a faint, lasting imprint on the black hole's immediate surroundings. This single idea could resolve the paradox. Information would not be lost. It would simply be translated into a form we are only just learning to read, woven into the fabric of spacetime itself. The universe, it seems, may keep perfect records after all, even in its most violent corners. This idea of a gateway leads us to one of the most breathtaking unknowns of all. The crushing core of a black hole might not be a final stop, but a portal. According to some brilliant and daring interpretations of the very equations Albert Einstein wrote, the heart of a black hole could contain a tunnel. Physicists call this an Einstein-Rosen bridge, though you likely know it by its more popular name, a wormhole. Picture a piece of paper representing the fabric of our universe. The distance from one side to the other is vast, but what if you could fold that paper, poking a tunnel directly through the center? That shortcut is the essence of a wormhole. It would be a cosmic subway connecting two incredibly distant parts of our universe in an instant, or perhaps even serving as a doorway to a completely different cosmos altogether. This is not just science fiction. The mathematics allows for it, yet a colossal problem immediately arises. The wormholes predicted by these classical equations are catastrophically unstable. They would snap shut in a fraction of a second, far too quickly for even a single particle of light to make the journey. Anything trying to pass through would be crushed in the violent collapse. So how could such a tunnel ever be used? The theoretical answer lies in something called exotic matter. This is not antimatter or dark matter, but a hypothetical substance with truly bizarre properties. Unlike everything we know, exotic matter would possess negative energy or negative pressure, effectively pushing space outward. If you could line the throat of a wormhole with this exotic matter, it could theoretically prop the tunnel open, resisting the immense gravitational forces that want to slam it shut. While no one has ever found or created such matter, its possibility keeps the dream of cosmic travel alive. Could some black holes be these stable tunnels, their interiors held open by laws of physics we do not yet understand? The idea transforms them from terrifying pits into the universe's ultimate potential crossroads. Yet even these potential gateways are not eternal. The universe seems to have a rule that nothing can last forever, not even a black hole. This brings us to one of the most profound discoveries in theoretical physics, an idea that completely rewrites the destiny of these cosmic giants. Stephen Hawking made the stunning calculation that black holes are not truly black. They glow. The source of this faint light is not from within the event horizon, but from the chaotic quantum foam that fizzes at its very boundary. Empty space, according to quantum theory, is not empty at all. It is a seething sea of virtual particles, pairs of matter and antimatter that constantly pop into existence and then annihilate each other in an unimaginably short flash. Normally, this happens without a trace, but when this quantum dance occurs right at the edge of a black hole's event horizon, the extreme gravity can tear these particle pairs apart. One particle falls irretrievably into the abyss, while its partner escapes, stealing a tiny amount of the black hole's energy to become a real particle racing out into the universe. This stream of escaping particles is Hawking radiation. It is an incredibly slow leak, a faint whisper of heat from an object we thought was the ultimate cosmic freezer. For a black hole with the mass of our Sun, this process of evaporation would take far, far longer than the current age of the universe, but the implication is absolute. Black holes are not permanent, they have a finite lifespan. They slowly shrink particle by particle over eons, and this leads to a final, mysterious end. As a black hole nears the end of its life, its evaporation rate speeds up dramatically. Theorists suggest its final moments would be a sudden, violent burst of energy and particles, a final pop as the last of its mass is converted into a flash of radiation. What would we see in that ultimate instant? Would the event horizon simply vanish, revealing whatever secret lay at its core for one brilliant fraction of a second? Or would it leave something else behind, a relic of spacetime we cannot yet conceive? The slow, cold death of a black hole may hold the key to its hottest, most explosive secret. This peaceful journey to the center, however, might be a comforting illusion. A terrifying new idea has emerged from the depths of quantum theory, one that turns the event horizon from a silent threshold into a wall of pure fire. This is the firewall paradox. According to our classical understanding of gravity, crossing the event horizon should be uneventful. You would not see a blazing wall or feel a sudden jolt. You would simply float past that invisible point of no return, with the true drama of spaghettification happening much deeper inside as the tidal forces finally pull you apart. But when we apply the strict rules of quantum mechanics to this scenario, a nightmare unfolds. The calculations suggest that the empty space just at the event horizon should be fizzing with such immense energy that it would act like a searing curtain of high-energy particles. Anything or anyone crossing that boundary would be instantly incinerated, reduced to a burst of radiation. This is not a gentle glow like Hawking radiation, but a concentrated inferno. The paradox is born from a brutal conflict. General relativity guarantees a smooth, continuous space where you can cross the horizon without noticing. Quantum mechanics, protecting the law of information conservation, seems to demand this violent firewall. They cannot both be correct, so what would you actually encounter? Would you be peacefully stretched on a cosmic rack or vaporized in a flash of quantum fury? The existence of a firewall would mean that black holes are not just dark voids, but objects shrouded in a cloak of unimaginable heat, fundamentally reshaping our understanding of their nature. Resolving this standoff is one of the most urgent puzzles in all of physics, forcing us to ask if our most trusted laws of the universe break down at the very edge of reality itself. The terrifying possibility of a firewall is not the only surprise waiting at the edge. A black hole's true power is not just in its gravity, but in its spin. When a massive star collapses, it does not just vanish into a static point. Many of these stars are already spinning, and like a figure skater pulling in their arms, their rotation accelerates as they collapse. The result is a Kerr black hole, a cosmic vortex spinning at a staggering fraction of the speed of light. This is not a gentle rotation. It is a whirlpool so violent that it does not just warp space, it grabs hold of it and drags it along for the ride. This creates a bizarre region just outside the event horizon called the ergosphere, a flattened, pumpkin-shaped zone where the fabric of spacetime is forced to move with the black hole's rotation. Within the ergosphere, it becomes impossible to stand still. The universe itself is flowing past you, like trying to remain motionless in a raging river. Every object, every particle of dust is compelled to move in the direction of the spin. This phenomenon, known as frame dragging, is so extreme that it warps the very definition of here and now. But this cosmic carousel is not just a spectacle. It might be the key to an almost unimaginable power source. A brilliant thought experiment proposed by physicist Roger Penrose suggests a way to actually steal energy from a black hole. Imagine an advanced civilization sending a probe into the ergosphere. The probe releases a payload which splits into two pieces. One piece is directed to fall into the event horizon, while the other is flung back out. Due to the insane physics of the ergosphere, the piece that falls in can have negative energy from the black hole's perspective. To balance the cosmic books, the piece that escapes must carry away more energy than the probe originally had. The black hole itself loses a tiny bit of its rotational energy, slowing down ever so slightly while the escaping fragment is supercharged. It is like bouncing a ball off a moving train. If the train is coming toward you, the ball bounces back with far more energy than you threw it with. In this case, the moving train is the very fabric of spacetime, and the black hole is paying the energy bill. This Penrose process transforms a black hole from a simple consumer of matter into a potential engine, a galactic power plant of staggering proportions. What could a civilization do with such a source of energy? The possibilities are as vast as the spinning darkness that makes it possible. But nature might have a strict dress code for these cosmic monsters. A principle known as cosmic censorship hypothesizes that every singularity must be clothed, forever hidden behind the modest veil of an event horizon. This is not just a cosmic preference, it is a necessity for the orderly function of the universe as we know it. The laws of physics, the very rules governing cause and effect, depend on predictability. They require that we cannot see the naked insanity of the singularity itself. But what if the veil was torn away? Imagine a point of infinite density, a true singularity, existing completely exposed to the rest of the cosmos. This theoretical object is known as a naked singularity. It would be a hole in the fabric of reality, a place where gravity becomes so infinitely strong that spacetime curves to a sharp point. With no event horizon to protect the outside universe from its bizarre core, the known laws of physics would simply break down. The predictable chain of cause and effect, the idea that every action has a reaction that we can understand, would cease to have any meaning. At the boundary of a naked singularity, time could loop back on itself, or gravity could become repulsive. The universe's rulebook would be ripped to shreds. The question of whether such an abomination can actually form is one of the most profound in theoretical physics. Do the laws of gravity naturally conspire to always wrap a protective event horizon around a singularity, effectively censoring its infinite weirdness from our view? Or could a particularly violent collapse or the merger of two rapidly spinning black holes create a singularity so wild that it bursts through its horizon, exposing its impossible heart? If a naked singularity did exist, it would be the ultimate cosmic anomaly, a window into a realm without rules. The search for dark matter has long been a ghost hunt through the cosmos. We see its gravitational grip on galaxies, holding them together with an invisible hand, yet we have never identified what it actually is. But what if the answer is not a new, exotic particle, but something far more tangible and far more ancient? While most black holes are born from the deaths of massive stars, a different kind could have been forged in the universe's first frantic moments. These are primordial black holes, and they are nothing like their stellar cousins. They could have condensed directly from the extreme densities of the Big Bang's aftermath, forming not from collapsing stars, but from the raw, churning energy of creation itself. Their sizes would be wildly different from anything we see today. A primordial black hole could be as small as an asteroid, yet contain the mass of an entire mountain or even a planet crushed into a speck smaller than a single atom. This is the key to their potential role. Because they are not made from stars, they could be almost anywhere, drifting unseen through the vast emptiness between stars or even through our own solar system. If they are abundant enough, their collective gravity could be the very dark matter glue that binds galaxies and shapes the large-scale structure of the universe. We would be living in a sea of these ancient relics, their combined mass outweighing all the visible stars and galaxies put together. The hunt is now on to find them. How could you detect something so small and dark? You would not see it directly. Instead, you would watch for its gravitational lensing effect, a tiny, fleeting magnification of a distant star as a primordial black hole passes in front of it, warping the starlight like a cosmic magnifying glass. Other searchers look for the telltale ripples in space-time they would create when they collide, or the final bursts of Hawking radiation they would emit as they evaporate after ages of silence. Finding just one would be a monumental discovery. It would solve two profound mysteries at once, revealing the nature of dark matter and opening a direct window to the very first second of our universe's existence. But the solitary life of a black hole is often an illusion. In the crowded cores of galaxies, these giants are drawn together in a final, catastrophic dance. As two black holes spiral inward, locked in a gravitational embrace, they do not merge quietly. They shake the very fabric of the cosmos, sending out ripples known as gravitational waves. These are not waves of water or sound, but literal stretches and squeezes of space itself, traveling outward at the speed of light. For most of the process, this energy radiates away symmetrically. But in the final, violent instant of merger, when the two event horizons become one, the emission can become a cosmic cannon. If the final burst of gravitational waves shoots out more strongly in one direction, it acts like the thrust from a rocket engine. To conserve momentum, the newborn, more massive black hole is kicked in the opposite direction, recoiling from the blast that forged it. This is not a gentle nudge. The kick can be so powerful it launches the black hole at speeds exceeding 5 million miles per hour. At that velocity, it easily escapes the gravitational pull of its entire host galaxy. Imagine a single dark object weighing many times the mass of our Sun, being flung out into the vast, empty darkness between galaxies. It would become a ghost ship, a rogue black hole drifting forever through the abyss, leaving no light in its wake. Its only trace would be the faint gravitational lensing of distant starlight it might pass in front of, a fleeting distortion revealing its impossible journey. These hypervelocity exiles are a direct result of the most violent events since the Big Bang, proving that even the universe's darkest monsters can be thrown out of their homes. This paradox strikes at the very heart of reality, questioning whether the universe keeps perfect records. If you burn a book, its information is not truly gone, just transformed into smoke and ash. In principle, a being with godlike knowledge could reverse the process and read every word. Quantum mechanics insists this is a universal law. Information is never destroyed, only scrambled. Yet a black hole, according to classical theory, appears to be the ultimate exception. It swallows a star with a unique composition, a specific history, a one-of-a-kind atomic structure, and seemingly offers only 3 bland facts in return: mass, spin, and charge. The rest is erased. This is the black hole information paradox in its purest form, a direct conflict between the rules of the very large and the rules of the very small. So where could the information possibly be hiding if it is not truly lost? One breathtaking possibility is that it is not inside the black hole at all, but painted onto its surface. The holographic principle suggests that all the information about everything that falls into a three-dimensional black hole is encoded on its two-dimensional event horizon, like a cosmic DVD storing a three-dimensional movie on a flat surface. The event horizon would be a vast pixelated screen, each Planck-sized area holding a single bit of information, a permanent fossil record of everything that ever crossed the threshold. Another solution lies in Hawking radiation itself. Perhaps the radiation is not completely random. Maybe it is subtly imprinted with the information of the particles that fell in, like a ghostly whisper carrying the secrets of the interior out into the universe. As the black hole evaporates over eons, it would slowly and meticulously release this encoded data, preserving the cosmic ledger. The information would escape, but in a form so scrambled and thermalized that it is effectively useless to anyone trying to read it. The universe would have kept its promise, but in the most cryptic way imaginable. Resolving this is not just an academic exercise. The answer will ultimately tell us whether reality is fundamentally predictable and orderly, or if true, irreversible chaos can exist in the darkest corners of creation. A black hole's distortion of space creates more than just a dark shadow. It can forge a cathedral of light. All objects with mass warp the space around them, bending the path of any light that travels nearby. But a black hole takes this to an absolute extreme. Its gravitational field is so intense that it acts as a natural cosmic lens, twisting and magnifying the light from stars and galaxies that lie directly behind it from our viewpoint. The result can be a perfect circle of light hanging in the void, an Einstein ring. It is a mirage on a galactic scale, a single distant object whose light is bent around the black hole's dark silhouette from all sides, meeting our telescopes as a halo of fire. Sometimes, if the alignment is not perfect, you do not see a full ring, but multiple distorted images of the same galaxy, arranged like ghostly copies around the central darkness. But the true spectacle unfolds even closer to the abyss. Around a spinning black hole, the warping of spacetime becomes so severe that light itself can be forced into a temporary prison. Just outside the event horizon lies a theoretical boundary called the photon sphere. Here, gravity is so perfectly tuned that photons, the particles of light, are sent into orbit. They do not spiral in and they do not fly away. They travel in unstable, circular paths around the black hole, tracing a brilliant ring in the sky. This would be a band of pure, trapped starlight, a celestial carousel where the universe's fastest thing is forced to run in circles. Step just inside this sphere and light falls inward forever. Step just outside and it can eventually escape, bent but not captured. To an observer, this would manifest as a dazzling, razor-thin ring of fire, composed of every star and nebula whose light has been snatched from its journey and compelled to orbit the darkness. It is a place where reality itself becomes a hall of mirrors, and light is forced to dance on the edge of oblivion. Even these galactic titans cannot feast forever. We marvel at supermassive black holes, behemoths with the mass of billions of suns, and wonder if their growth is truly infinite. Is there a point where a black hole simply cannot get any bigger? The answer may lie not in the black hole itself, but in the very process that feeds it. Imagine a cosmic bonfire raging just outside the point of no return. This is the accretion disk, a swirling maelstrom of superheated gas and dust spiraling inward at nearly the speed of light. As this material is shredded and compressed, it glows with unimaginable brilliance, outshining entire galaxies. This light, however, carries a force. The radiation pouring from the disk creates an outward pressure, a relentless cosmic wind that pushes against the very matter trying to fall in. For a truly gluttonous black hole, this process can become self-limiting. The more it eats, the brighter its dinner plate glows, and that intense light can eventually blow away the surrounding gas and dust, cutting off its own food supply. The black hole effectively starves itself into a state of equilibrium, its growth stunted by the fury of its own consumption. But there is another, more profound limit to consider. A black hole can only grow as fast as matter can fall into it, and the universe has only a finite amount of time and material. Even if it could devour every star in its galaxy, there is a theoretical maximum mass based on the age of the cosmos and the distribution of matter. Some calculations suggest an ultimate upper bound, a point where no more gas can cool and flow toward the center to be consumed. Yet the true ceiling remains one of cosmology's great unknowns. Do the very largest black holes we see represent this natural limit, or are they simply paused, waiting for a new cosmic chapter to begin their feast anew? That final, violent merger is not a silent event. It rings across the cosmos. When two black holes collide and become one, the newborn object does not simply sit quietly. It wobbles violently, its very shape oscillating like a struck bell. These vibrations are not sound waves traveling through air, but something far more fundamental, ripples in the fabric of spacetime itself, gravitational waves. And just as a bell's unique shape and size determine the pitch of its ring, a black hole's mass and spin define its own specific frequency, a phenomenon known as its ringdown. As the newly formed black hole settles into a stable sphere, it radiates these gravitational waves, ringing out its own unique signature across the universe. Scientists can now translate these space-time vibrations into sound waves our ears can perceive. The result is a rising chirp, a cosmic song that begins slowly and quietly, then rapidly rises in both pitch and volume before abruptly cutting off. That cutoff is the moment the black hole becomes perfectly smooth and stable, its ring down complete. Each chirp is a direct audio fingerprint of an invisible monster. By analyzing the precise frequencies in this ring down, researchers can measure the final mass and the incredible spin of the resulting black hole with astonishing precision. This is our only way to directly hear these dark objects, a new sense granted to us by the most violent events in the universe, allowing us to listen to the echoes of spacetime itself. The ringing of a newborn black hole fades, leaving behind an object whose true nature defies our most basic assumptions about density. We are taught to picture a singularity of infinite density, a point where all the mass of a star or a galaxy is crushed into a space smaller than an atom. But this picture is incomplete, focusing only on the terrifying core. To understand a black hole as a whole, we must consider its average density, a simple calculation of its total mass spread across the entire volume inside its event horizon. And this is where the universe delivers one of its greatest surprises. A black hole's size is not fixed. The more mass it has, the larger its event horizon grows. This relationship is not linear. The radius of the event horizon increases proportionally to the mass, but the volume inside that sphere increases far more dramatically. The result is a breathtaking inversion of logic. A small, stellar mass black hole is incredibly dense on average. But a supermassive black hole, like the one at the heart of our own Milky Way with the mass of 4 million suns, has an event horizon so vast that its average density can be lower than the air we breathe. Imagine all the mass of millions of stars spread throughout an immense spherical volume. The vast majority of the space inside that event horizon is just that empty space, punctuated only by the unfathomably dense singularity at the very center. It is a cosmic palace with a nightmare in its basement, a realm where the true extremity is confined to a single, infinitesimal point. This means you could, in theory, cross the event horizon of a supermassive black hole and not even realize it for quite some time, floating through an immense, dark void before the central gravity finally begins to pull you apart. The monster's lair is not a cramped, crowded pit, but a cavern of deceptive emptiness hiding its ultimate secret deep within. Yet even these immense voids might have a cosmic counterpart. If a black hole is a one-way street where everything enters and nothing leaves, then a white hole is its theoretical mirror image, a place where nothing can ever enter, but matter and energy can only pour out. Think of a black hole as a cosmic drain and a white hole as a cosmic fountain gushing endlessly into the universe. This is not mere science fiction. White holes pop out as perfectly valid, if bizarre, solutions to the very same equations of general relativity that predict black holes. They are the other side of the mathematical coin. But if they are allowed by the laws of physics, why have we never seen one? The problem is one of time and stability. A white hole would be an event that violently ejects all of its mass and energy in a single explosive burst and then simply ceases to exist. It is a cosmic flash in the pan, a momentary rupture in spacetime that might be impossible to form naturally after the Big Bang. This leads to a staggering possibility. What if the single most important event in our cosmic history, the Big Bang, was itself a white hole? The initial singularity, a point of infinite density, could be reinterpreted as a white hole erupting, spewing out all the matter and energy that would eventually form every galaxy, star, and planet. Our entire universe could be the outflow from a primordial white hole. An even more mind-bending idea connects them directly to the black holes we know. Some interpretations of wormholes suggest that the tunnel through a black hole does not end in a singularity, but instead opens out into a white hole in a completely separate universe. In this view, every black hole that forms in our cosmos could be birthing a new universe through its white hole counterpart. The matter we see falling in here might be the very material of creation somewhere else. So the terrifying collapse of a star could be a genesis event in another reality, transforming the ultimate end into a magnificent beginning. Gravity may be the black hole's defining force, but it is not the only power at play. Deep within the swirling chaos of the accretion disk, another fundamental force is at work, shaping the very environment for light years around. Magnetic fields generated by the frantic motion of superheated, ionized gas become trapped and twisted by the black hole's immense spin. They don't just float there passively, they are stretched and wound into colossal coils, transforming the area around the black hole into a cosmic power plant. These magnetic fields channel some of the infalling matter, not down into the abyss, but outward in two narrow, incredibly focused beams. These are relativistic jets screaming away from the black hole's poles at nearly the speed of light. Composed of a searing plasma of electrons and other subatomic particles, these jets can punch straight through the surrounding galaxy, stretching across distances so vast they defy human comprehension. We see them as brilliant lances of radio waves and X-rays, sometimes longer than the galaxy they originate from. Their influence is profound. Where these jets slam into clouds of cool gas, they can trigger the birth of new stars by compressing the material. In other regions, they can have the opposite effect, violently heating the gas and blowing it away, preventing stars from forming at all. A single black hole through these magnetic conduits can act as a galactic architect, its reach extending far beyond its event horizon to dictate the life cycle of stars across its entire cosmic neighborhood. The central mystery is how the black hole itself sustains this incredible magnetic dynamo. Is the energy drawn directly from its ferocious spin, or is it a more complex dance between the inflowing matter and the space-time it drags along with it? The answer lies hidden within the storm, a secret written in magnetic lines of force. The extreme gravity of a black hole does more than bend space, it twists time itself. Near the event horizon, the fabric of space-time is stretched so thin that time slows to a crawl. Imagine an astronaut on a daring mission, skimming just above the point of no return. For every single hour their clock ticks forward, decades or even centuries could be passing for everyone else in the universe. They would return to a future unrecognizable, having time traveled into the world of their distant descendants. This is not science fiction, but a direct prediction of Einstein's theory of general relativity known as time dilation. Gravity is not just a force that pulls, it is the very geometry of reality, and where that geometry is most severely warped, time itself becomes elastic. The closer you get to an immense gravitational source, the slower your clock runs compared to a distant observer. A black hole is simply the ultimate expression of this principle, a place where time can nearly stand still. But the true theoretical wildness emerges with a spinning black hole. Its whirlpool of distorted spacetime could, in theory, create pathways known as closed time-like curves. These are not tunnels through space, but loops in the very timeline. An object following such a curve would find that every possible path through spacetime leads back to its own past. It could, in essence, meet itself from an earlier moment. While most physicists believe effects at the quantum level would prevent such paradoxes from actually occurring, the mere fact that our best theory of gravity allows for the possibility is staggering. It reveals that the flow of time, which feels so absolute and linear to us, may be a fragile local condition, not a universal law. That smooth, definite boundary of the event horizon might be another comforting illusion. Quantum mechanics paints a far stranger picture of reality at its most fundamental level. It tells us that even in a perfect vacuum, space is never truly empty or still. It is a seething, bubbling foam, a realm of constant uncertainty where pairs of virtual particles flicker in and out of existence in a frantic, unpredictable dance. When we apply this quantum rulebook to the edge of a black hole, the very idea of a sharp mathematical boundary begins to dissolve. The event horizon may not be a clean line you can cross, but a blurry, roiling transition zone, a quantum fog of unimaginable activity. Physicists call this a fuzzy black hole. In this view, the horizon is not a static wall, but a dynamic, fluctuating surface, alive with extreme quantum jitters. This fuzziness could be the key to solving the most profound paradox of all. Remember the terrifying firewall, the idea of a searing curtain of energy. The fuzzy horizon offers a different, yet still violent, solution. Instead of a single, sharp wall of fire, the boundary becomes a vast, churning region where quantum fluctuations are so intense that they scramble and encode the information of anything that passes through. Think of it not as a brick wall, but as a raging waterfall. As matter falls toward the black hole, it hits this turbulent quantum cascade. It is utterly torn apart, but its fundamental information, the unique blueprint of what it was, is not erased. It is imprinted onto the chaotic, fizzing structure of the fuzzy horizon itself. This quantum froth acts like a fast-acting cosmic hard drive, recording the identity of everything that falls in. Then, as the black hole slowly evaporates via Hawking radiation, this stored information is not lost. It is meticulously released back into the universe, carried away by the escaping particles. The radiation is not random noise after all. It is a complex, encoded message, a slow broadcast of all the secrets the black hole has ever consumed. The fuzziness resolves the paradox by providing a physical mechanism, a structure that can store and eventually transmit information, preserving the universe's quantum rulebook even in the face of its darkest monsters. So the event horizon is not a silent, sharp edge, but a roaring, fuzzy processor, tirelessly working to uphold the most fundamental law of all, that information, the story of what is and what was, must never be allowed to vanish. This invisible engine at the galactic core holds a power far beyond its minuscule size. A supermassive black hole, while containing the mass of millions of suns, is physically tiny compared to the 100,000 light-year expanse of its host galaxy. Yet, this speck of ultimate darkness acts as the galaxy's master regulator, its beating heart dictating the very life cycle of stars. When a black hole actively feeds, the colossal energy released does not simply vanish into the void. It creates a powerful feedback loop, a cosmic conversation between the monster and its home. The intense radiation and those focused relativistic jets pour unimaginable energy into the surrounding clouds of cold, dense gas, the very raw material for new stars. This interstellar nursery is violently heated. the gas particles sent flying apart with such vigor that they can no longer collapse under their own gravity to ignite new suns. In the most extreme outbursts, the black hole can even blast this gas completely out of the galaxy, stripping it of its future stellar fuel. This process effectively puts a ceiling on the galaxy's growth. It is why we do not see ancient galaxies endlessly spawning new generations of stars, becoming impossibly large and bright. The central black hole acts as a built-in thermostat, preventing the system from overheating with stellar birth. But this relationship is a two-way street. The same gas flows that feed the black hole and allow it to grow are also the material for new stars. A delicate balance exists. Too much feedback and the galaxy is quenched, its star formation shut down. Too little, and the galaxy might overconsume its gas in a burst of frantic starbirth, leaving nothing for the future. This intricate dance explains a profound mystery: why the mass of a galaxy's central black hole is so closely related to the mass of the galaxy's central bulge of stars. They did not grow independently but evolved together, locked in a gravitational embrace, one dictating the limits of the other across billions of years. The largest structures in the universe are forever shaped by the smallest and darkest of objects. The hunt for these cosmic giants has always focused on two extremes, the small and the supermassive. Yet a ghost haunts the middle ground. For decades, astronomers have searched for a missing link, a black hole of intermediate mass. These would be the middle children of the dark family, weighing between 100 and 100,000 times the mass of our Sun. They are the theoretical stepping stones, the crucial rungs on a ladder that could explain one of the universe's most puzzling growth spurts. How did the supermassive black holes at the center of galaxies become so immense so quickly when the cosmos was still young? Stellar mass black holes, born from collapsing stars, are simply too small to grow that fast on their own. They would need to feast for far longer than the age of the universe to reach billions of solar masses. But if they could instead find and merge with pre-existing intermediate mass black holes, the path to becoming a supermassive giant becomes clear. These IMBHS would be the seeds of the cosmic monsters we see today, the foundational blocks upon which galaxies built their dark hearts. The challenge has been catching one in the wild. They are quieter than their supermassive cousins, often residing in the sparse globular clusters that orbit galaxies, not blazing with the light of a vast accretion disk. Their darkness makes them nearly invisible, yet the universe has begun to offer clues through the faintest of tremors in spacetime. Recent detections of gravitational waves have included events that are difficult to explain with stellar mass black holes alone. Some of the ripples point to collisions that created black holes firmly within this elusive intermediate mass range. Each signal is a potential sighting, a whisper from the darkness suggesting these missing links are out there, drifting in the cosmic voids and occasionally crashing together. Finding more of them, confirming their existence, is now one of astronomy's most pressing quests. It would complete our family tree of black holes and finally reveal the hidden growth strategy of the universe's most dominant structures. A black hole's power is not limited to gravity alone. It can also hold a fundamental force of nature within its grasp. While most black holes are thought to be electrically neutral, the mathematics of general relativity allows for a fascinating possibility: a black hole with a significant electric charge. This theoretical object is known as a Reissner-Nordström black hole. Its existence would fundamentally alter the space around it. Unlike the single, simple event horizon of a standard black hole, a charged one would be structured like a cosmic onion, possessing two distinct layers. There would be an outer event horizon, similar to what we know, and within that, a second, inner horizon. The space between these boundaries would be a strange and violent region, a battleground between the immense pull of gravity and the powerful repulsion of the electric charge. Crossing the outer horizon would still be a point of no return, but the journey inward would not be a smooth descent. As you approach that inner horizon, the very fabric of spacetime could become unstable, with the combined effects of gravity and charge creating a zone of infinite energy density. Some theories suggest you might not even reach the central singularity, being torn apart by these warring forces in the space between the horizons. Yet for all its theoretical ferocity, a charged black hole is likely a fleeting phantom in our universe. The reason lies in the cosmos's relentless drive toward balance. Any black hole that somehow acquired a strong electric charge would immediately become a powerful magnet, violently attracting particles of the opposite charge from the surrounding interstellar plasma. This cosmic cloud of free-floating ions and electrons would rush in to neutralize the charge, effectively short-circuiting the black hole in an instant. The universe seems to prefer its monsters to be simple and dark, not electrically alive. So while the equations permit such a beast, nature's own cleaning crew may ensure they are among the rarest of all cosmic anomalies. This intimate link between a black hole and its galaxy hints at a deeper, more fundamental connection woven into reality itself. To uncover it, we must venture to the edge of the event horizon and peer into the quantum fog. There we find physics at its most bizarre, where the very concept of a separate here and there breaks down. This is the realm of quantum entanglement, a phenomenon Einstein himself famously called spooky action at a distance. When two particles become entangled, they are no longer independent individuals. Their fates are inextricably linked, such that measuring a property of one particle, like its spin, instantly determines the property of the other, no matter how far apart they are in the universe. It is as if they share a single existence. Now, bring this quantum strangeness to the precipice of a black hole. Remember the virtual particle pairs that fuel Hawking radiation. One falls in and its entangled partner escapes, but here lies the core of the information paradox. If the escaped particle is part of an entangled pair, what happened to its partner inside the black hole? According to quantum rules, entanglement is a sacred bond. It cannot be simply broken, yet from the outside, it seems the black hole has severed this connection, violating a fundamental quantum law. This is not just a minor puzzle. It is a crisis that demands a radical solution, and the answer may reshape our understanding of reality. A stunning proposal known as ER equals EPR suggests a way out. It posits that quantum entanglement and the fabric of spacetime are not just related. They are one and the same phenomenon seen from different perspectives. The acronym ER refers to Einstein and Rosen, the physicists behind the original wormhole idea, while EPR stands for Einstein, Podolsky, and Rosen, who first highlighted the paradox of entanglement. This idea boldly claims that every pair of entangled particles is actually connected by a microscopic wormhole, a tiny bridge in the geometry of spacetime itself. Think of two entangled particles not as separate objects sending spooky signals, but as two ends of the same cosmic subway, a shortcut so profound that distance becomes irrelevant. Now apply this to our black hole paradox. The entangled pair at the event horizon, one inside and one outside, are not communicating across a vast divide. They are connected by an Einstein-Rosen bridge, a wormhole threading through the black hole's interior. The information about what falls in does not vanish. It travels through this wormhole connection, preserving the entanglement and thus the information. The event horizon, in this view, is not a destructive wall but a tapestry of countless microscopic wormholes, each one a thread of quantum connection. This means the universe might be fundamentally woven together by an unimaginably complex web of entanglement, and the geometry of space we see is just the large-scale manifestation of these quantum threads. The black hole is no longer a monster that breaks the rules, but the ultimate expression of how deeply quantum mechanics and gravity are intertwined. Could it be that every connection in the cosmos, from the smallest particles to the largest galaxies, is held together by these hidden tunnels in the fabric of reality? The slow, cold whisper of Hawking radiation guarantees that even the mightiest black hole has an expiration date. But what happens when the last of that mass has finally evaporated away? Does the darkness simply wink out of existence, leaving nothing behind? Or is there a final, indestructible relic left over? The theoretical endpoint of this cosmic evaporation remains one of the greatest puzzles in physics. Some models suggest the process cannot run to absolute zero. Instead, as the black hole shrinks to a minuscule size, the evaporation might slow to a crawl, leaving behind a stable remnant no larger than the smallest possible unit of length in the universe. This Planck mass remnant would be a frozen cinder, a permanent fossil containing the final echoes of the black hole's original mass. It would be the universe's ultimate time capsule, a grain of sand holding the secrets of a mountain. Yet other theories propose a far more dramatic finale. The black hole could shrink until it reaches a point of instability and then vanish in a final, blinding flash of high-energy radiation. Everything, including the central singularity, would cease to exist, but this scenario forces a confrontation with the most sacred rule of quantum mechanics. If the black hole vanishes completely, what happens to all the information it ever consumed? The story of every star, every atom, every bit of cosmic history that fell in would seemingly be erased from the universe forever. This cannot be. The laws of physics demand that information is never truly lost, only transformed. So if the black hole vanishes, the information must go somewhere. Perhaps it is encoded in that final, explosive burst of radiation, scrambled into a code so complex it is practically unreadable but preserved nonetheless. Or maybe the information is transferred to a baby universe that pinches off at the final moment, carrying the data away into a separate reality. The true endpoint of a black hole's life is more than a curiosity. It is the very key that could unlock a unified theory of quantum gravity. By understanding what happens in that last brilliant flash, we might finally see how the fabric of spacetime is woven from the threads of quantum information itself. The quantum entanglement of a black hole's event horizon is not the final word on the paradox. A startling new idea has emerged from the world of theoretical physics, a concept so strange it redefines where a black hole's surface truly lies. Physicists call these regions islands, but do not picture landmasses in a sea. These are not physical places you could visit. An island is a region of spacetime deep within the black hole's interior that, through the bizarre rules of quantum gravity, becomes entangled with the radiation streaming out into the distant universe. In a stunning twist, the calculations show that this distant radiation and the island inside the black hole are so deeply linked that they are, in a quantum sense, the same surface. The information that fell into the black hole is not trapped on the event horizon we see from the outside. Instead, it is pinned to this quantum island deep within the abyss. And because the island is entangled with the outgoing Hawking radiation, the information it holds is not lost. It is slowly and meticulously transcribed, carried away from the interior by the very radiation the black hole emits. Imagine a secret message written on a piece of paper locked inside a vault. The vault has no doors or windows, yet every word on that paper is somehow mirrored onto a second piece of paper outside, its ink drawn from the vault's own fading heat. The island is that internal piece of paper, and the Hawking radiation is the external one. This means the interior of the black hole is not a sealed chamber of oblivion. Parts of it are in constant, spooky communication with the far future of the outside cosmos. The paradox finds a potential resolution not by breaking the rules, but by accepting that the universe's quantum connections are far more profound than we ever dreamed. The event horizon is not the true boundary of information. The black hole's memory is kept safe on a quantum shore, an island in the dark, ensuring that no story consumed by the darkness is ever truly forgotten. The serene darkness of the event horizon is a profound illusion. Just outside that point of no return rages a cosmic hurricane of incandescent gas and pure energy, a region known as the corona. This is the black hole's seething atmosphere, a place of unimaginable violence where temperatures can soar into the billions of degrees. We are not talking about the swirling accretion disk here, but a superheated plasma hovering above it, a shroud of pure fury enveloping the abyss. This corona is the source of the most powerful X-rays in the universe, a constant high-energy scream announcing the black hole's presence across the cosmos. How can a place so close to the ultimate cold of the event horizon become so impossibly hot? The answer lies in the raw power of magnetic fields. The chaotic motion of the accretion disk twists and amplifies magnetic field lines into colossal, unstable coils. When these lines suddenly snap and reconnect, in a process similar to what happens on our Sun but on a vastly more energetic scale, they release a catastrophic burst of energy. This magnetic explosion heats the surrounding electrons to near light speeds, forcing them to slam into photons of lower energy light and supercharge them into blistering X-rays. It is a continuous, self-sustaining storm, a natural particle accelerator of staggering power. By studying the flicker and flash of this X-ray light, astronomers can map the corona's structure and behavior. Sometimes it is a compact, brilliant source hovering right above the black hole's pole. Other times it expands into a wider, fainter halo. These changes reveal the dynamic and unstable nature of the magnetic fields, offering us a real-time window into the physics of accretion. The corona is the final, furious processing plant for matter before it vanishes forever, transforming the potential energy of infalling gas into a torrent of radiation that illuminates the darkness. What other secrets about the fundamental forces of nature are being forged in this relentless atmospheric inferno? That searing corona and its magnetic fury are just the beginning. The true particle accelerator lies in the gravitational heart of the vortex itself. A spinning black hole does not just warp space, it energizes the very vacuum around it, creating conditions for collisions of staggering power. While our most advanced machines on Earth, like the Large Hadron Collider, smash protons together at incredible speeds, they are toys compared to the forces at play here. The Penrose process we explored earlier shows how energy can be extracted, but there is another, more violent possibility. Imagine two protons drifting in the chaotic maelstrom of the accretion disk. The black hole's immense gravity, especially its frame-dragging effect in the ergosphere, can act like a cosmic slingshot, hurling these particles to velocities that approach the absolute limit, the speed of light. If two such particles are sent on a collision course, the energy of their impact would be unimaginable. It would dwarf anything we could ever create. This is not just a bigger boom. At these extreme energies, physicists believe we could reach the Planck scale. This is the smallest possible size in the universe, the fundamental resolution of reality itself. Probing this scale would be like switching on a light in a room we have only ever known through the cracks in the door. We could witness the quantum nature of gravity firsthand, seeing if spacetime itself is made of discrete grains, and potentially uncovering the unified laws that govern all forces. A black hole, then, is not merely a destructive pit. It is a natural laboratory, a cosmic forge where the fundamental secrets of existence are hammered out in bursts of raw energy. What profound truths about the universe are being revealed in these fleeting, invisible collisions at the edge of oblivion? These cosmic behemoths at the center of galaxies present a timeline problem. The universe was not old enough for them to grow so large from mere stellar seeds. To reach masses of billions of suns when the cosmos was just a baby, they must have been born big. The leading theory points to a different kind of birth entirely, not from a dying star, but from the direct collapse of a primordial giant. Picture a vast, pristine cloud of hydrogen and helium from the early universe. Normally, such a cloud would fragment, birthing a glittering cluster of stars, but under the right conditions, this fragmentation could be suppressed. The gas cloud, perhaps weighing tens of thousands of solar masses, would collapse as a single monstrous entity. There is no supernova, no final defiant blast from a dying star. Instead, the entire cloud falls inward upon itself, silently and cataclysmically, directly forging a massive black hole seed in one single staggering step. This seed, already thousands of times heavier than any stellar black hole, would have a colossal head start, allowing it to balloon into a supermassive giant within the first billion years of the cosmos. Another possibility lies in the crowded, violent nurseries of the first star clusters. Here, in dense stellar cities, many smaller black holes could have formed and then rapidly merged through a chaotic gravitational dance, building up an intermediate mass object that would later sink to the galaxy's center and continue its feast. Yet both theories face challenges. The conditions for direct collapse had to be just right, and the merger path is messy and complex. The origin of these galactic titans remains one of cosmology's most pressing puzzles, forcing us to question what other monstrous shortcuts the young universe allowed in its frantic first moments. That silent boundary surrounding the abyss could be the most complex hard drive in the cosmos. The holographic principle takes the strange idea of information storage at the event horizon and stretches it to a universal scale. It proposes that our perception of a three-dimensional world with its depth and volume might be a magnificent illusion. Everything we see and experience, every star, every planet, and even ourselves, could be a holographic projection from a vast, two-dimensional surface at the edge of our cosmic horizon. Think of watching a movie on a high-definition screen. The image has depth and movement, characters that seem to walk into the distance, but all of that information is stored on the flat, two-dimensional surface of the screen. The holographic principle suggests our universe operates in a similar, though far more complex way. The event horizon of a black hole becomes the perfect testing ground for this breathtaking idea. All the information about the incredibly complex three-dimensional space inside the black hole, every atom of the stars that fell in, could be perfectly encoded on its two-dimensional surface. This is not a blurry approximation, but a perfect one-to-one translation of reality. The event horizon would be pixelated, not with squares of light, but with the smallest possible units of area in the universe, each one holding a single bit of information. This resolves the black hole information paradox in the most elegant way possible. When matter falls in, its information is not destroyed. It is simply translated and painted onto the surface of the event horizon like a cosmic tattoo. As the black hole evaporates via Hawking radiation, this information is slowly and meticulously released back into the universe. The holographic principle forces us to confront a staggering possibility. The solidity of the world around us, the very feeling of depth and space, might be an emergent property, a consequence of complex information processing happening on a distant, two-dimensional surface we cannot see. If true, this would mean that the fundamental building blocks of reality are not particles or strings, but bits of information. The universe is not made of stuff, it is made of data. And a black hole is not a pit of annihilation, but the universe's most efficient data storage device, challenging everything we assume about the nature of existence itself. So what truly happens to a star, a spaceship, or even a single atom in its final moments inside this darkness? We have followed its journey past the firewall, through the quantum fuzz, and toward the crushing core, but its ultimate fate remains the greatest secret a black hole keeps. The classic answer is the singularity, that point of infinite density where all the fallen matter is crushed into a volume of zero size. Every proton, every neutron, every quark is thought to be squeezed out of existence, its identity erased in a final mathematical oblivion. Yet infinity is a concept that makes physicists deeply uneasy, a sign that our equations have broken down. Perhaps matter is not destroyed, but radically transformed. Think of ice melting into water or water boiling into steam. Each phase change creates a new state of matter with entirely different properties. The interior of a black hole could be the site of the most extreme phase change in the cosmos. The incredible pressure and density might force atoms to dissolve into a soup of their fundamental building blocks, quarks and gluons, creating a perfect frictionless fluid. Or it might compress everything into a solid crystal of pure energy, a state of matter so dense and strange it exists only in theory. Another possibility is even more profound. What if the matter is not transformed into a new substance but becomes part of the stage itself? The fabric of spacetime is not a static backdrop, it is a dynamic physical entity. The immense mass and energy of everything that falls in could be woven directly into this fabric, adding new threads to the cosmic tapestry. The black hole would not be a pit but a loom, relentlessly spinning the stuff of stars into the very structure of reality. This would mean that you, me, and every star we see are not merely moving through space, but are potential material for its continuous creation and expansion. The final secret may be that there is no final state, only an endless process of reinvention, where the line between the actor and the stage blurs into nothingness. What falls into the black hole does not vanish, it becomes the universe. From their theoretical quantum hair to their staggering potential as cosmic portals, black holes stand as the ultimate testament to how much we have yet to learn. These 30 unknowns are not a checklist of solved puzzles, but a map pointing toward the very frontiers of physics. They reveal that these are not merely the silent graves of dead stars, but dynamic, evolving engines that actively sculpt the cosmos, from birthing new universes to governing the life cycles of galaxies. They are the one place in the universe where our two most powerful theories, the cosmic lawbook of gravity and the quantum rulebook of the very small, collide in a spectacular and unresolved conflict. Unifying them is the holy grail of modern physics, and the key almost certainly lies hidden behind an event horizon. So we leave you with a final question, one that has echoed through this entire journey. Which of these profound unknowns captured your imagination the most? Was it the possibility of a white hole birthing a new reality, the terrifying paradox of the firewall, or the sheer mystery of what truly happens at the final singularity? Share your thoughts in the comments below. If these cosmic enigmas have sparked your curiosity, please like this video, subscribe to the channel, and hit the bell so you do not miss our next exploration into the deepest mysteries of the universe.